In this video, we'll discuss the heap insert and delete min operations of a heap data structure. So let's see how we do that. The overall idea is that we first, at first step, what we do is that we maintain the structure property of the heap, and and we insert a new node into the heap using the structure property. Of course, the value could be smaller. That could be the minimum value in the tree as well. So what we do is that we perform an operation that is called percolate up, or we also, in some literature, we find the term heapify. We heapify this value up to its desired or its intended location. Okay, so the last value that we inserted, at the first step we inserted by maintaining the heap structure property, and then we heapify it upwards until it finds its actual location. So the idea, how we do it, is that if this is a almost complete heap tree, and we want to insert value 14 into this tree, what we do is that, and remember, this is implemented into a tree, into an array. So if this is inserted into an array, this root node is at index 1, index 2, index 3, similarly index 4, 5, 6, 7, 8, 9, 10. So what we do is that inside the array, we have the data up till the index 10. Okay, what we do is that we have this array of a bigger size, and we have some free space here. We simply add 1 to the last index and reach at the index number 11, and insert this or store this new value at index number 11. So now this 14 has become the child of 11 divided by 2 is index number 5. So at index number 5, we should have this value 31. So index number 5, we should have this value 31. Okay, so if we just recheck, index number 1 is a root, 2, 3, 4, and 5. So index number 5 is 31, and adding a value at index number 11 is the right child of index 5. So 14 becomes the right child of index 5 of the value 31. So 14, we just insert it here and increase the size of this heap by 1. Okay, initially the size was 10, now the size is 11. Okay, for the next insert, what we would do is that we would increase the size by 1. Size plus 1 is index number 12, and we would add the new value at index number 12. Then if we want to add another value, we would simply add 1 to the size of the heap and reach the index 13, and we store the new value there. But if you see here is that at this node number 31, this heap order property is now violated. This 14 is a smaller value, it should be up in the tree. Okay, should not be the child of 31, because the heap order property says that the parent should always have a smaller value than the child. Okay, so the second step is to heapify this value upwards. So by heapify, what I mean is that I would compare this new value with its parent. If the value is smaller than the parent, then I swap these values. 14 goes upward, 31 goes down at the index number 11. Okay, but we should not stop here, because 14 could be a very small value, or maybe the smallest value in this tree. So this process goes upward and it would only stop when the parent of this 14 is a smaller value. So when the 14 reaches here, it would be compared with 21. Again, 21 is bigger value, so another swap is performed. 14 which is at this position. Okay, 21 is here, 31 is here. So this operation is the heapify up operation. So at this position, when 14 is compared with 13, 14 is a bigger value. So this satisfies the heap order property of the heap. So 14 would stop here. So this heapify operation, it would go upward in the tree until it finds the position where the parent is smaller than the 14. Otherwise, it can go up to the root as well. That's how a smaller value reaches up in the tree. Or we adjust the value in the tree according to its priority or its key. Okay, so that's the actually animation. 14, it's compared with 31 and it's smaller, so it moves up, 31 goes down. For the next step, what it does is, now see, this is the first swap, now this is the second swap. In the second swap, 21 moves down, 14 goes up. And then the last comparison is also performed, but no swap is performed there. So this is the position where 14 resides for the inside the heap. Okay, until an element is removed from the heap. So that is the insert operation. Now let's move on to the next operation, that is the delete min in the heap. So this delete min operation is also using the heapify or percolate operation, but this time it's slightly different. In fact, this time the delete operation uses this heapify the other way around. So how it does it, that the minimum element that is to be removed is always on the root. So we remove the root of the tree. So if I remove the root of this tree, what I have is two subtrees, which means that I need to pick either one of the child to take the position of this root node and connect this entire structure. All right. So similarly, but if I just pick this node or a smaller value among these two to take the position of the root node. For example, if this left child is a smaller value, then this goes up, and I can again pick a smaller value from the further two children at the below level. For example, if this value goes up in at this position, now I have a hole at this location which violates the structure property of the heap. Okay, so this naive approach does not work here. Similarly, we cannot just take the right side child of the root, because this could be a bigger value than the left child. So this idea of just replacing the root with either of its children or with the smaller child is not a good idea. Instead, what we should do is to adjust the entire structure so that it maintains the structure as well as the heap order property. So what we would do here is that we would move the last element, that is this element, up in the heap to the root. So if this element goes to the root, this was a bigger element. How can it stay on the root? Which means this is not the correct position for this element. But what we should do is that now we do is that we ask this value to be compared with the children. So the smaller child, if even if it's the left child, it goes up, and but this time it would be a swap operation. So with the swap operation, we have a new value down in the tree, and then we perform another swap here, we move another value here. So a hole is not created in that case. So this is the idea how we maintain the structure as well as the heap order property of the delete min of the delete in the heap. So let's see just an animation. So if I want to delete the minimum element, that is the root, I delete 13. I would replace this 31 here. Okay, so deleting 13 is that we move 31 up in the heap and we just decrease the size of heap by 1. So the next insert operation works fine. So we move 31 up in the tree, right? And when we move 31 here in the tree, we compare it with its children, and we find that the smaller children is the child is this 14. We swap this 14 with 31. Then we further check it with the children. Now the smaller child is 19. We swap 19 with 31. Then we check again with the children. The smaller value is 26. So we replace or we swap 26 and 31. So the final heap is this one, the 31 that went up to the root. It goes down and reaches this leaf level. But in this way, we have removed a value from the far right end of the array, and we reduce the size of this array by 1. So that's how we delete an element from a heap. And the implementation in C++ is very easy. So I would not go into the details of the C++ implementation of this operation, because this is just manipulating an array, and that's what any C++ uh, proficient programmer can do very easily. So that's the operation, that is percolating down or heapify down. Okay, so that's the end of the two operations, insert and delete min.